Now come to the part of line of sight received power calculation. So for that you require this LED power, like I have shown you earlier. If we calculate received power, it is simply transmitted power multiplied with line of sight channel gain. So first we have specified the value of LED, or you can say this is the PT power. So this is the example value I have taken in watt is 0.15 watt. You can take 2 watt, 3 watt, as per the your system model you can take different values. So this value we have specified, and line of sight channel gain we have calculated earlier based on the LED parameter and the receiver parameter. Similarly, come to the PD part. As you know, this line of sight channel equation is validated, which is the value of m plus 1 upon 2 pi dij square cos m phi cos xi. So this value is valid for the incidence angle value which lie within the field of view of the receiver. After that, if your psi angle is greater than the field of value, the channel gain will be 0. So we need to also specify the field of view of the PD. So again I have specified this value in radian here. You can also use the degree value here, so that this 30 degree. So generally the standard value of receiver field of view we take as 60 degree. You can change this value, there is no issue in that. So this is how you give the value of, you need to give the value of field of view of the receiver. Next, again when we calculate this received power, there is also a term ARX, like what is the PD surface area of the photodetector. So anything that is in the equation you need to give as a input form. So so generally this value lies in 10 to the power minus 7 centimeter square, or you can convert into centimeter square. You can take any practical value here. And again the bandwidth of the system. So here we have taken 10 megahertz system. So we have specified the bandwidth value of 10 to the power 6. And again as you need to this speed VLC system, if there is a transmitter, there is a receiver. So to receive this signal there is a concentrator which capture the signal. So based on that, this refractive index of that particular optical lenses that you are using, that value we have specified here, because it is like in order to calculate this equation, it is multiplied with T psi and the G psi. These are the optical concentrator and acceptance angle gain. So in order to calculate this optical concentrator, you require the value of refractive index, because it follow that particular equation, n square divided by sin square psi c. So this is the practical value 1.46 we have taken for the photodetector concentrator gain. And then this is the gain of lens. Generally we take this value 1. You can also take any practical value like I have mentioned here, 10. So as you know, this signal from, like if this is the transmitter plane, the LED is mounted here, which is transmitting the power at the LED semi-wave angle of 5/2, and suppose this is the receiver plane and there is a PD here which is receiving the signal, and if it is an indoor room there will be a wall with some reflectivity, suppose of 0.5. So you will receive two signal. One will be the line of sight signal and another will be the non-line of sight signal, which is reflecting from the wall with angle suppose alpha and beta, and suppose this distance is DLOS and this is D1 and D2. So in order to model this non-line of sight channel gain, you need to model this reflection. So this reflection can be one point reflection, in which the LED first getting reflected 1 point from the wall and received at the PD, and it can be of 2-point reflection where light is reflecting from 2 point at the area and then again receiving at the receiver. So for that you can use this geometrical method to model this non-line of sight reflection, or you can use that infrared diffused model where we considered the same reflectivity inside the room. So every NLOS channel gain have the same value. So in two ways you can model this non-line of sight reflection. So again you need to give the mathematical input as MATLAB require. So again this is the room size that we have specified, 5 cross 5 of 3 meter. This is the floor reflectivity. This is the reflection can get from the wall, 0.7, and this is the reflection that we can get from the ceiling. So these are the parameters values for the non-line of sight reflection. Now in order to calculate this SNR, with respect to the P received power, you also require noise variance. So for that you require this noise parameter. As I mentioned earlier, there will be a short noise, there will be a thermal noise. So these are the different factor, like this I2 is noise bandwidth factor, data rate you are operating on, ambient light power, because ambient light behave as a noise to the receiver in case of visible light communication system, photodetector responsivity, in what percentage your light will be converted into electrical signal, then the electronic charge, and the amplifier bandwidth in terms when we are going to include this amplifier noise. So these all are the practical values. You can follow any reference paper, or as per your system requirement you can give them as a input to the system. And again the amplifier noise in ampere per hertz. Okay, now we are going to simulate the line of sight channel gain. So the first thing, as you know, line of sight channel gain equation is m plus 1 upon 2 pi dij square cos m phi cos psi PD gain, optical PD gain, concentrator gain, and this xi should be in the range of 0 to field of view of the receiver. So the first thing you need to simulate is Lambertian parameter or Lambertian order. So m is nothing but natural log of 2 divided by natural log of cos of semi angle. So this is simply we have mentioned here, and we have already mentioned the value of phi earlier. So this phi again is limited within the LED semi angle value. So this is how you can get the value of m, Lambertian order. Next will be now based on this Lambertian model you can calculate the radiation intensity, which is nothing but m plus 1 2 pi cos phi m. So we already know the value of m, we have already given the input value of phi. So now based on this radiant intensity we can finally able to calculate this line of sight channel gain with the receiver area of ARX. Again this h distance, as I have shown you earlier, this h distance is equal to your dij. So this is how you are able to simulate this particular line of sight equation. So based on that, if you have this line of sight channel gain value, so in VLC your received power is nothing but transmitted power multiplied with line of sight channel gain, and we have also already specified this transmitter or LED power earlier to the power R square. So this is how So if I write complete equation here, so it will be PT ARX m plus 1 upon 2 pi dij square cos m phi cos xi multiply with g psi and t psi. So now you are able to, so this particular vector P received line of sight will give you the line of sight channel gain value, and the order of this vector will depend on the number of LED as well as how you have divided your receiver floor, how many number of grids. Like in our case we are going to divide into 25 cross 25 subgrids. Now earlier we have calculated this line of sight channel gain. Now we are going to calculate non-line of sight channel gain with the help of Lambertian model. So in Lambertian model, as I have shown you earlier, if this is the transmitter plane and this is the receiver plane, and if this is the wall and you have this PD, the LED is mounted here which is transmitting with the again semi angle value of 5/2. So the received signal will be from non-line of sight will be like this. It is taking the distance d1 from LED to the reflection point of the wall, and to receive the PD it is taking distance d2, and this is the incidence angle to the wall alpha, and if this is the angle of incidence or reflection which is making with respect to the PD is beta. So now you are going to give these input values d1, d2, alpha and beta. So how we can do it? So again I have shown you earlier, like you have divided to cover the whole room, you need to divide the room into number of grids and you will calculate the power at each grid. So you require the distance of LED to each grid. Similarly, in order to get the reflection from the whole wall, you need to divide this wall into the number of grids, and from each grid you will calculate these distances d1 and d2 and find out the value of alpha and beta. So for the same you can run a loop which is ranging from nx to ny. Nx and ny are the number of grids that you are dividing, and this is the receiver position we have specified here, which will vary in x and y coordinate and remain constant in z coordinate. And based on that receiver position, so first to store the value we have specify a vector h1 which will store the value of non-line of sight reflection gain from each grid. So this is how you can calculate this distance d1. So d1 will be nothing but a distance from transmitter to the receiver plane that light has taken. So this is how we have in order to calculate these distances d1, d2 and these angle alpha and beta, what you required? You required the transmitter position, you required the wall position vector, or you can say the coordinate, and you required the receiver position. So receiver position we have already specified earlier. So based on this transmitter position vector and wall position vector, you can calculate this respective distance. So these are nothing but distance that we calculate with the help of Pythagoras prometheus, like if two coordinate, like one point at x1, y1 and z1 and another one at x2, y2 and z2, so then the orthogonal or the minimum distance between them can be calculated as x2 minus x1 ka whole square plus y2 minus y1 ka whole square. So the similar method we have approached here in order to calculate those distances d1. Now based on those distances you are going to calculate these respective value alpha and beta, because if you have gone through this non-line of sight channel gain equation, it is defined as area of the wall, the area of the point from where your light signal is getting reflected multiply with m plus 1 divided by 2 pi d1 square d2 square cos m phi cos alpha cos beta and g psi t psi. So now in order to simulate the non-line of sight channel gain with respect to the line of sight channel gain, you require two distances d1 and d2 square, and you require two angles alpha and beta, and this beta is equal as the reflection angle xi. So again this your beta should be lie within the field of view of the receiver in order to perfectly convert your optical signal into a electrical signal. If any of your signal lies outer that field of view of the receiver, if this is the field of view of receiver, if any signal lie outside this, it will not be able to convert into any electrical signal. So this is how we have calculated distance d1, d2 and the respective angle alpha and beta. And based on this, like you can see here, we are able to calculate this alpha, we also able to calculate this angle beta, and based on that, so this is the simple channel gain equation I have written here, which I have written here. So here will be the m plus 1. So we have already specified this vector which are going to store these non-line of sight channel gain value. Add these. So what will happen? The loop will run for the number of grids. In each grid, whatever will be the channel gain value will be stored in this particular vector h1. So this is how we simulate non-line of sight channel gain if we are following this Lambessian order model. So there are other model exist like diffuse channel model, non-line of sight channel gain as a diffuse. So in this case we consider the non-line of sight channel gain with the equal reflectance from each wall. So for that you require this. So the room dimension of suppose has length L and has width W and height of H. So based on that floor area, wall area and ceiling area, you can calculate the overall channel gain. So if you can see here, the diffuse channel gain, you calculate first the overall reflectivity. So which is nothing but rho equals to 1 divided by area of the room multiply with the floor area into n reflectance from the floor plus wall area reflectance of the n wall plus ceiling area and their respective reflection coefficient. So based on that, your overall effective reflectivity will be nothing but I1, which is the channel gain, or you can say the illumination intensity divided by 1 minus rho. So this is, so in diffuse we do not consider instant reflectivity, we consider overall reflectivity. So this model generally used in infrared communication, we can also use it for visible light communication as well. So as you shown, if you have a mathematical expression available with you, you can use other different model also, like 2-point reflection model, 1-point reflection model, or this diffuse channel model respectively. So again, if you have this overall reflectivity available, so your received power will nothing but be the transmit power divided by the room area multiply with rho 1 minus rho, and again you need to multiply with the area of the room and the respective distances square. So this is how so what is the benefit with the VLC channel modulation is it is not random in nature. It simply follow that particular mathematical equation, or you can say it can be random if you introduce human blockages inside it, then this distances will become the function of human blockages location. But if you have equation available with you, you can easily give them as an input and you can calculate the respective values. Now, so based on that, now you can calculate the received power. So again, as I have mentioned earlier, this will be the PD concentrator gain G psi, which is defined as n square sine square field of view of the receiver. We have already defined the reflectivity of the medium and the field of view of the receiver. So based on that, now as I have shown you earlier, the transmitter plane in VLC, the receiver plane, the total power will be sum of line of sight channel gain and the non-line of sight channel gain. So your total power P received will be transmitted power multiplied with HLOS plus NLOS multiplied with respective PD gains. And if you multiply PD inside it, this will simply P received because of line of sight path plus P received with non-line of sight path multiply with TF and G, and we have already defined the value of TF and the G psi. So this is how you can get the total received power. And as you know, we have considered a 3D room here. So your output P received total will be a 3-dimensional vector. So you will get a matrix which will be of order of M cross N cross P. So these value of M, N and P depends on the number of grids that you have considered inside the room. So again, you can plot the received power value with lens, where you can use this lens gain, or you can plot it without lens also. So just to compare the received power, how it looks like with lens and without lens. Obviously this without lens will be the worst one, and with lens you can get the improved power or improved received power. And this will be with the diffusion, with the diffusion, because in the diffusion you are considering both line of sight and non-line of sight as a common factor or the common reflectivity. So it will simply be the P received diffuse multiplied with the respective lens gain. Now, in order to do the SNR calculation, we are already calculated received power. Now we require the noise variance. Now this noise variance has three types of noise there. Short noise, as I have mentioned earlier, thermal noise, and the amplifier noise. Now, in order to simulate in MATLAB, what you required mathematical expression of short noise, which is again in case of indoor VLC system, it is a function of received power, and then the thermal noise and the amplifier noise. So we have already defined all the noise parameter. What we are going to do here, we are going to simply write their respective equation, and we have given the input of their parameters, so we can get the value in vector form. Like we have defined this noise bandwidth I2 into RB, where RB is the data rate, and then the ambient light power, which is the ratio of ambient light intensity divided by the R, radius of the room, and then the short noise, simply, if you know, it defined as 2Q R responsivity into the P received plus P ambient multiplied with noise bandwidth, Bn. So we have simply written the equation of the short noise. So you will get a vector omega short, which will represent your short noise, and then the amplifier noise, which is nothing but I amplifier square into divided by the amplifier bandwidth. So this is the amplifier bandwidth, we have already defined it. Then the thermal noise variance. So this long expression you can see in any book. So you can simply write that particular expression and define every variable that here you need to define it first. And based on that, you can get the total noise. So this sigma square VLC will be the sigma square short plus sigma square thermal plus sigma square amplifier. So now you have calculated this total noise power as well. So now you can easily calculate the SNR, which is nothing but the P received divided by sigma square VLC. So as I've said, your SNR will be the function of received power divided by the total noise. Now, as we have mathematically simulated all the parameters which required in VLC, like received power, noise variance, and the SNR. Now, one by one, we are going to plot it, and we are going to see how, by changing the different parameter, these parameters varies. So first we are going to study channel gain as a function of PD position. So you can see here we have plotted this HLOS. HLOS you can refer in previous slides. So you can see here these are the PD position from 0 to 1.5 to minus 1.5, and this is the channel gain HLOS. So you can see here, by varying the LED semi-angle value, your channel gain varies. And as you know, it is a function of cos of LED semi-angle. So as cos function value maximizes for the smaller value of angle and it minimizes for the larger angle of value. So you can say for LED semi-angle value of 15 degree, the channel gain is maximum, or you can say it is of increased value. And as you increase the value from 15 to 30, the channel gain value reduces. So this is the variation, like your maximum channel gain value start decreasing if you start increasing the LED semi-angle value. But with increase in LED semi-angle value, your channel gain value reduces, but the distance that it covers, it increases. So it means there is a trade-off. Wider LED semi-angle value will cover the more distance. You can see here it will able to cover, you can say minus 1.5 to 1.5. So effectively you can see it can cover 3 meter radius with the angle of 60 degree. But if you see for 15 degree value, it is only able to cover from minus 0.75 to plus 0.75, or you can say the effective value of 1.5 radius. So you can see there is a trade-off. Wider LED semi-angle value give you the lower channel gain with the larger coverage, and smaller LED semi-angle value give you the lower coverage with the maximized channel gain. So you can itself, by changing the value of these LED semi-angle, you can plot these. And again, the receiver parameter like field of view we have considered as a 70 degrees. So it is a wider PD that we have considered here. Now again, you can see the variation by changing the field of view also. So this is, so here if I remove this, you can see here we have plotted here is a again the channel gain, but for the smaller field of view. So again you can refer to the equation. Your channel gain is also a function of incidence angle xi, and again it is a function of cos, where xi is limited between the field of view of the receiver. So again, smaller the field of view, larger will be the gain, but the distances you cover will be less, and the wider the channel gain, you can cover more distances but with the smaller channel gain. So this is how you can play with your LED semi-angle and field of view of the receiver, and you can analyze for different configuration, and you can use for your as per application. Now we are going to plot the 3D receipt power profile. So this is the receipt power profile with one LED. It means in this case the LED is mounted on the center of the room. So you can see here the maximum power is at the exactly below the where the LED is placed, which is 10 dBm, the maximum power that we are getting. And as we are going towards the edge of the room, as the distance vector will be increasing, like this will be the minimum distance, which is exactly the line of sight, and as we go towards the edge of the room, the distance increases, so the receipt power starts decreasing. So this is with the, when your LED is mounted on exactly center of the room, this is how your you can say the receipt power looks like. And if we go for the, suppose we want to plot this for 4 LED configuration, where this like your LED is mounted in rectangular configuration, as we have mentioned earlier here. So how our receipt power will look like? It will be like this. So the receipt power will be maximum exactly where LEDs are deployed, and again start decreasing as the distance increases. So there will be a, so you can consider like it is symmetric in nature. So it's simply the one LED configuration for this each sub coordinate, and it is a overlap. So and the area where they are overlapping, it will be a improved performance. So again at the corner of the room, the power is minimum, and the LED where it installed, will be the maximum. So again for the simulation of this, the total power we have considered of 2 watt, which is constant. This is the 1 LED configuration, and this is the 4 LED configuration, and you can see you have improved in receipt power. So in this case, the maximum power that we are able to receive is 10 dBm, while here we are able to receive the power value of 12 dBm. So again, this is for the LED semi-angle value and the field of view value of 60 degree. Both these profile, 1 LED and 4 LED. You can plot it with different LED semi-angle configuration. You can see the variation. Like in our work, we have tried to plot this with improved LED semi-angle value, or you can say the optimized lambation order. So this is the 1 LED configuration with phi optimized as 58 degree, and again this is with the 4 LED configuration with again phi LED optimized as 58 degree. So this is the standard value that we have calculated. You can also calculate this optimum LED semi-angle value as per your configuration and see the receipt power profile. So you can see this is the receipt power is more uniform in nature with respect to the other power profiles that we have calculated, and again the field of view we have kept constant as 60 degree. So you can see these variation with yourself also by changing these value. Now as we have calculated this receipt power profile, so with the help of this receipt power profile, you can also analyze the delay spread performance of the system. So the delay spread actually the function of your received channel gain only. So as we generally know, we define or characterize our delay spread with the RMS delay spread, and which is nothing but T HT divided by the minus infinity to plus infinity H square T, or you can say the average. So here in order to calculate the RMS delay spread, you are going to require this channel gain, which we have already calculated with the help of line of sight simulation model and the non-line of sight simulation model. So you can use those channel gain value here and plot this delay spread as well. So for that, first you need to define this time resolution in nanosecond, because for what time instant that you are going to analyze your system, and then based on that you can get the time vector in nanosecond. So here we have taken the time resolution value of 1/2, or you can say the 0.5, and based on that first you define this H vector, which is firstly it is a vector of 0 value, and as you run the loop, because for the delay spread analysis you need to consider all the channel gain values, and so that in each iteration that this vector value will be added here. So this is the T vector, and this is the mean delay spread, because you are going to divide this mean delay spread divided by the mean square delay spread, and based on that you can get this RMS delay spread. So this is nothing but a simple delay spread expression that we have written here. This will be the mean delay spread, mean delay, and this is the mean square RMS delay spread. So based on that, now you have this delay spread. Again, it will be a 3-dimensional vector because your channel gain is a 3-dimensional vector. So based on that, you can also plot this delay spread. So you can see here for different LED semi-angle, we have plotted this delay spread. So the maximum value of delay spread that we are getting is 0.35 nanosecond. And as we have optimized this LED semi-angle, we have reduced this delay spread from 0.35 to 0.15 nanosecond. So this is again for 4 LED configuration. This is also for 4 LED configuration. So as we know, the delay spread is a function of channel delay profile or the channel gain. As the distance from the LED to the detector increases, the delay spread will also increase. So you can see at the center of the room, unlike receive power profile, the delay spread is minimum, and at the corner of the room, unlike receive power profile, the delay spread is maximum while receive power is minimum. So there is a trade-off in visible light communication. At the center of the room or exactly below the LED, you will get the received power profile maximum, but the delay spread will be minimum because channel will take less time to travel to the PD. And at the edge of the room, the received power profile will be minimum and the delay spread will be maximum. So this is how we can characterize our indoor VLC system with the help of MATLAB, where we can calculate this received power, and based on the received power you can calculate the signal to noise ratio, which will help you in plotting the bit error rate or the outage probabilities. And based on that, you can also study the delay spread analysis, which will helpful in order to analyze your interference system or inter-symbol interference. So in this lecture, we have studied how we can simulate this indoor VLC channel model with the help of MATLAB. Thank you.